Okay, so although we have analyzed the results and in the Fluent and also in the CFX CFD post, but I want to be sure that the solution is accurate or not. So I just checked it. So by double clicking on solution, it will open the Fluent. It is opening the mesh file and case file and as well as the data file which we saved in the previous time. And keep in mind that the first order upwind scheme is always a diffusive scheme, and the results might be very much different than the what we are expecting. So you must ensure that the momentum equation is set to second order upwind scheme. So this is the problem here. And so all other steps will be same, everything will be same. Only thing difference here is that we are now going to run the second order upwind scheme for momentum and simply click on calculate. So the only thing you will see in the difference in terms of that is in terms of results, that you will see the maybe there are some changes, maybe you can see the some separation, maybe you can see the more mixing, more turbulence, more heat transfer rate transfer from the hot fluid to the cold fluid. So we will wait for solution to be completed and then we will go back to the CFD post and see that how they are different from the further scheme. And as you can observe that the regular plots are there now straight line, which are they are already done, are there in the very just in the beginning. But if you take a look on the points plots at the different locations for the temperature, and this is also another point, this is also another point, and you can see that these are now almost straight lines. See here, and maybe some variation is in the plot number 0. But I can see that because in the previous cases we also seen that these small variations in the results, there was some small fluctuations. So I think this is that we can consider this one as a solution now converged, and therefore it's a time to stop the solution and check the results. And as you can see that the solution is now stopped. And the most important thing in this video is that we want to check the effect of the second order upwind scheme, that is from the momentum equation, on the solution. And that's the if you go through literature or through the papers or books, you will see that the scheme has the very pronounced effect on the results. So you always run the case with the second order upwind scheme, and if you go with the first order, so you will have the that is called that is known as the numerical viscosity, and you will see the results will be diffused, and you will not get the sharp gradients for example for the viscosity, for the shock wave, for the density. And so whenever these are very important for you, so in that case you must ensure that you should go for second order scheme. And the second thing is that with the second order upwind scheme, the results will be more accurate. So first thing is that the gradients are sharp if you go with the second order upwind scheme, and second thing is that results are more accurate with the second order upwind scheme. Okay, so I will just check the results in the Fluent, and you can see that in the previous case the temperature has was just on the incline on the one side here, but in the second order scheme you can see that you have the proper distribution of the temperature which is captured here, and this is all over this whole plane. And now you can see the effect of this solar on the mixing process and the heat transfer rate. And if you take a look on the velocity, so effect here, so it means that either we have the no separation or the flow is fully mixed here. And if you take a look on the vector plots, and that is on the same plane, and you can observe that the velocity vector shows you that there's separation or there's no separation. In this case I don't see any separation, as all velocity vectors are going in a straight line, and there's no reverse direction for these vectors. So I assume that with the second order scheme there's no separation, that's why it is not captured here. And if we go with the pressure contours, and also you will see that we have the more accurate representation of the pressure as well, and especially in this zone. where we see the more gradients of the pressure. Okay, now it's time to analyze these results in the CFD post. And for that, simply double click on the results, and you can see that we have these two green arrows in the curvature. This shows that something is changed, and now we need to update that thing also in the results. And obviously the results are changed from the solar part, and now the CFD post will load all the new results, that is with the solar, and without solar definitely the results are same. So in the second case, we run the case with the second order upwind scheme for the momentum. So I will just wait for the solution to be loaded into the CFD post. Alright, so you can see that we have the more turbulence is captured here, and also you can see that we have these two vortices which are present in the without solar, that is coming from the small pipe, and also we have these two vortices which are present in this part. And in this case, because of swirling effect or this, that has mixed the two flows very nicely, and therefore you don't see any vortices or swirling flow in the upper pipe portion of the mixing elbow. And if you analyze them based on the contour plots, so let's plot them, and I will hide the streamlines. This is a velocity contour plot, and so I have to revisit the contour plot that is on the surface 8, and that was at a 0 location for the Z. That is in fact symmetry plane if this model was off model. The second thing I want to see, this is without solar, this is with the solar. Yes, this is correct. Okay, so this is a local, and I can see that we have these plots with us, and this is the local, everything is all right. So maybe you can check for the advanced properties. This is the variable location, is a vortex. Okay, so this is all right. So maybe you can increase the number of contour plots. Let's say make it 40 or 50, and then see the contour plots. The second thing I want to see here is that the contour plots of the temperature, and we see the more effect here in this case. Otherwise, in the previous case with the further scheme, you can see that the solution was limited to only this portion. Now we can see that we have the more mixing, we have the more heat transfer, and definitely with the more mixing, with the more turbulence, and turbulence enhances the mixing, and more heat transfer. So this is the effect here. So you can also reduce the number of contour plots to the 11 to again back to that number. And if needed, you can also draw the contour lines which are already plotted here, but they have the same color as the color inside this contour. But if you want to make it black, let's say, you can make it as a constant, and you will see these contour plots with the color inside, and the outside we have these lines as the border lines. And the next thing is that I want to plot this let's say now we have this line here. So you can see that in this portion we have the more mixing, so I want to see the results, and for that I will use a chart number 3, and you can see that we have the velocity magnitude, that is over here. Okay, this is the temperature, and for the velocity I can change this to the velocity, and the velocity is now almost a constant value or almost a straight line. And as compared to the previous case without the solar, that has some maximum values and then some minimum values, but here in this case almost it's a constant. And if you plot the pressure, you can see they are almost same, but in the case of with the solar we can have the more pressure here. That's because of the more pressure is coming from the solar part, so this is very obvious. And for the temperature, again the same behavior. So in this way we have confirmed the solution with the second order upwind scheme, and it's very important to run the case. Number one is that they should be on the same conditions, same settings, and number two is that for any fluid flow problem or heat transfer problem, you must use the second order scheme for momentum equation, because this will give you the the highest possible accuracy, and the gradients will also be resolved very nicely and precisely. That's all for this case. And also I have added the one more video. That video is basically based on the location of this solar blade part, and right now it is at the 191 millimeter location from the bottom side. And the new case which you see in the next video, that is moved to the 291.